Okay, Desmos.com should have showed you this pattern that they go steeper and steeper and steeper based on the bigger the base is. Did you catch on to that? Okay, good. And they all touch right there. Why? Think for a second. That's at x equals 0. Think about it. Yes? Changing your mind? Yes? Because anything to the 0 power equals 1, right? They have to be. They'll have to go through 1 because they all go to the, when you put in x is 0, they all have to touch 1. All right, good. Moving on. These, when you graphed these, it was a little different. What do they all go through? They all go through 1 again. Why? Because anything to the 0 power is 1. That's why they keep going through 1. But this time, it's a matter of going down like this, right? Okay, now think about this. This is exponential decay, and it should be going down, right? We usually only think about this part of the decay, which is, in the first quadrant there. But basically, that's like the population of newts or whatever they are going down over time. Okay? And then the bigger the base is, isn't it the steeper it is? So in other words, was 1/5 the one that was super steep? Look on your graph once and tell me. Was it? Okay. So the bigger and I shouldn't have said the base. The bigger the bottom number is. So really what that means is the smaller this whole thing was, because 1/5 is smaller than 1/2, right? The smaller the whole thing was, the steeper it was. All right. I'd like to summarize it this way. If you had this 2 to the x, and this number gets bigger and bigger, the graph will get steeper and steeper. Steeper, 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 as that gets bigger. And if we look at it this way, that's growth, right? Because that's like 1 plus 1. What if it's like 1 minus 0.5? Okay, then that's going to be, as the growth or the decay rate gets bigger and bigger, the whole number will get smaller and smaller. Because if I got 90% decay, then that's going to be really steep. Okay, so this is also going to be governed by those same rules of stretching and moving and all that stuff. So if I had this 2 times 3 to the x minus 2 plus 7, the whole thing is going to be stretched twice as tall as it used to be. So will this one still hit 1? No, it's going to get twice as tall as that. It used to be 1, now it would be 2. Then it gets moved, what's that? Up 7, so the whole graph would have to move up 7. Then, what's that mean? Right 2. Good. And then this base, remember how we said before, is the bigger the base gets, the steeper it gets? So the bigger that is beyond 2, the steeper it is. Okay, so if you want it to be super steep, you have to have a base of like 10 or something. All right, so if I said, here is your typical one, 2 to the x, but then I did this to it, minus 3 here and plus 5 there, you should be able to write me what 2 things just happened. Up this and left that or whatever. I'll compare with the kid that's sitting near you and see if they had the same thing. Did you say right 3 and up 5? Okay, good. That's what we were looking for there. Now, if you were going to graph this by hand, that means obviously just you and the piece of paper and a pencil. You would want to make an XY chart because your life is so much simpler if you use an XY chart to keep track of these things. All right, so everybody make a little XY chart like this. And then we're going to pick a few logical spots for X. What is one spot you know we want to pick? X is what? X is 1, yes, but there was a special spot that they all went through when X is 0, yes. And X is 1, and X is 2, And then if we only have numbers that are getting bigger, it's not going to be as good as if we throw in a couple that are smaller, like -1. All right? If I put in 0, I don't have to like see the graph to do this. I can do it in my head. Anything to the 0 power is 1. Does that mean the entire thing is 1? No. That part I circled is 1, and then I times it by 2. 2 times the 1 makes 2. All right? I'd like you to figure out the next few points. Stick in 1 in here. Figure out the answer. Stick in 2. Stick in -1. I'd like you to stick in -2. That'll give us 5 points. Okay, as I'm looking at this, I'm thinking, all right, I know that this thing has a base of 3, so it's going to be kind of steep. And then this 2 in front means twice as tall as it used to be. And then this x power here means that it's an exponential, so that I know that this whole thing is generally looking like that. Now that's a rough sketch as opposed to graphing. If I graph it, I should actually take these points. When I stuck in 0, 2, I did hit that one. Yay. 1. When I stick in a 1 right here, 3 to the 1 is 3. 3 times 2 is 6. You should have had 1, 6. Over 1, up 1, 2, 3, 4, 5, 6. Do you see I missed pretty badly on my estimate? All right. Then it's 2. 2 goes in here. 3 squared is 9 times 2 is 18. Holy crap, that's way off the graph, and it's super steep. Okay, so I was definitely off in my little sketch. Now if I put in -1, sometimes kids forget what that means in this context. If I put in a -1 here, then that means 3 to the -1, which means 1/3. And then that's times 2, so it makes 2/3. How many of you had 2/3 for your answer for that? About 5 people. Okay. It's because you probably didn't know what to do with 3 to the -1. It's 1/3. All right, so if it's 2/3, -1 comma 2/3 means it should be about here. And again, I missed pretty badly on my green estimate. That's the difference between a sketch and a graph. So in my last one, -2, that's going to make 3 squared is 9, and then the negative makes it flip 1/9. So then I times it by 2. 2 times 1/9 makes 2/9. -2 comma 2/9 is just a ridiculously small number. So now I'm going to go, shoot, the red one is what it really should have been. Okay. Now, do you have to do it based on an XY chart? No, but it is the most accurate way to go. I could do it based on this. I know they usually go through one, and they're kind of like, they generally look like this. That's just a brief sketch. And I could generally say that this thing gets moved right to, because of this right here, and up to, because of that right there. So I'm going to take this dot right there and move it right to and up to with my line. Down to, right to, and down to, thank you. So then I'm going to grab this part of the graph and move it with my finger right to and down to, and there we go. That's a sketch. Again, if you want it to be accurate, though, you need an XY chart. And you'd stick in, remember, 5 points if you want to do a curve nice enough to actually, you know, be quality. 4, sometimes you can't get the 5th point to fit, like on this one. 2 comma 18 didn't fit on the graph, so we had 4 points, and that was good enough. Okay, so we try for 5, and if you can only get 4, then so be it. All right, so if I put in x is 0, 0 minus 2 is -2. 2 to the -2 is 1/4. And 1/4 minus 2 is a small negative number, -2. And now -1 3/4. Oof. So I got to go 0 comma -1 3/4. And that's about there. Hey, I actually hit that one pretty well. Okay. And then if I put in some other numbers that are going to work nicer, like maybe 2 would work a lot nicer. I'll put a 2 here, because then 2 minus 2 for the power is 0. 2 to the 0 is 1. 1 minus 2 is -1. 2 comma negative 1. Oh, I also hit that spot. My estimate wasn't too bad this time. I'm going to try another one. Let me put in 3. And again, you don't have to pick 0, 1, 2. You can pick 0, 2, 3. Start using numbers that work nicer. 3 to the minus 2 is 1. 2 to the first is 2. 2 minus 2 is 0. And so 3 goes with 0. I also almost hit that one. So I really wasn't too bad on my graph this time. I bet this last point's going to be off, though. We'll see. Put in a 4. 4 minus 2 is 2. 2 to the second is 4. 4 minus 2 is 2. And 4 comma 2 then should be on here. 4 comma 2. Yeah, I was kind of off on that one a little bit. But I wasn't too bad. All right. So if you're going to graph these, I don't want to put you through that because it takes a long time and I'd rather get you working on your assignment. But the main idea is you could make an XY chart and you could plug in numbers that would work nice. And right away I'm thinking I'd rather put in negative 4 to make my power equal 0. Get what I mean? Don't just start at 0. Start at a number that works nice. If I put in negative 4, it won't be that bad because then this whole thing becomes something to the 0 power, which is 1. And 2 times 1 is 2, minus 4, or minus 6 is negative 4, so negative 4 is on my graph. That's one of my points, and you'd have to find a few more. Generally, do you get these kind of go down like that because this is decay? Anytime you have something less than 1 in here, then you have decay, and it's going to be shrinking. All right, this one's decay, so it generally kind of looks like this, but it has a negative in front of it, which means the whole graph will have to flip. But if you trust and you do your XY chart nicely, it'll flip it for you, and it won't be that scary. Just have to do the points like normal. Okay, and then we'd have to move it too. It's going to be moved 3 to the right and up 4 after it gets flipped. Okay, moving on. So this is our last problem we have to do before we actually do some real-world questions like this. Mr. Best bought a boombox in 1986 for 80 bucks. This is interesting because I bought one in 1985 or 84. It might have been 1984. I had a boombox, and it was like to be able to play when I was shooting baskets in the gym. So I'd have it set up there, and then I still remember Sean. Thanks a lot, Sean, if you're listening. Was playing, and his basketball hit my boombox, and the handle was standing up on it, and it hit really hard, and it smashed the handle down in and broke the circuit board on the boombox. So he broke it, the punk. But it was expensive too, and then so I brought it to a guy who actually, back in those days, there were people that actually fixed electronics. I know there are still a few around today, but usually nowadays you say throw it away, buy a new one. But he actually fixed the boombox for me. Got a little welder out and soldered some things into the circuit board, and he got it to work again. Okay, anyway, the boombox lost 17% of its value until now. Well, for Pete's sakes. Oh, you mean it must mean every year, okay? Because otherwise, if it's just 17% down, there's no way. That boombox, you can get them at a garage sale now. You see them every now and then for $3 or whatever, and they probably cost $100 to start with. So they've depreciated a lot. 17% per year, I could believe. Make a set of axes and graph the value of the boombox from 1986 until 2000. That's really easy. Here's 1986, and here's the year 2000. And do you get that the value is going to go down, 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 down? Do you get that that's kind of like exponential decay? That's what's going on here. Okay? And how do you write these? You write them y equals the starting value goes here. And what was the starting value of the boombox? 80 bucks. Times, and then what goes in there? 1 plus or 1 minus, and in this case, 1 what? 1 minus because it's decay. And what? 17%. Does that make sense? They're going down 17%. And then you don't have to get creative with this x. It's just an x because this is an exponential problem, and so there's an x in the exponent. How do I know this one will go down? Because this ends up being a number less than 1. Anytime that happens, it's going to be going down. So generally, the graph kind of looks like that. All right. So if you were going to actually, you know, if I had this on a test, it says label the axes, so I'd have to label years. And this is dollars. And then here would be 80. That's one of my points that I know exists. And then maybe you'd go figure out, like, it says at least 2 points. Okay? So I could find a value here in the year 2000. Well, how many years has it been from 1986 until 2000? 14 years later. So I put a 14 right here, and I put it in my calculator, and I figure out how much is it worth then. So I go 80 times that 1 minus 0.17 to the 14th. Anybody with fast fingers have that already? Say it again. 5.89. $5.89 is what the boombox is worth now because it's depreciated so much. And that's honestly about right. Seriously, at a garage sale, you can get those old boomboxes for $5. So, all right. So there's a point. Here's another point. I know these actual points from the calculator, so they must be right. Could I have figured out a different point, like halfway? Sure. What would be halfway if it's 14 years? Or sorry. Yeah, it's not till now, it's till 2000. Halfway in there would be like 7 years later, which would be like 1993. Yeah, you could put in 7 here then and figure out the price in here somewhere. You don't have to, but if you wanted to, you could. But you have to have 2 points. All right, I think you get the idea. This was the hard part, making that equation. I'd like you to make one equation for me like that. Because if you can make the equation, the graph will be easy. You just use the calculator to find the point for you. All right, so here's a new scenario. And I want you to make me just an equation, right? Y equals whatever. And you're going to compare it with that kid that I paired you with for today. Okay. Let's talk about the moose population in Minnesota. It's an example of something that's decaying. Right now, their population has been going down. It's kind of scary. They don't know exactly why. Of course, some people say it's global warming. Some people say it's just because they have a tick problem. They are definitely finding these moose with lots of scars from them scratching themselves on things, and that's because they have these ticks. And the thing that's troubling about that to me, about whether or not that's global warming or not, is that over in Michigan, which is about the same latitude we're at, they don't have the tick problem, and the moose are fine. And so it's not necessarily that it just got warmer. Maybe it's these ticks are here and they're not there. And I don't know, why are they here? Maybe it's because of global warming. But then if it's just global warming, why aren't the ticks in Michigan? So anyway, we don't know for sure. But we know that the ticks are hurting the moose. And so here's my numbers for your equation. There's about 5,000 moose in Minnesota. But their population's been dropping by like 5% per year. The question could be, what will the population of moose be 10 years from now if this keeps up? So write me an equation. Starts with a y equals, of course. Pause for a second. I'm going to give that one a shot. All right, so that one came out to 2,994 with this equation. And I'm thinking that you are ready. So your assignment for today is the one under lesson 6. It's 11.6, I guess you could say, and it is graphing. Now, it's going to ask you for multiple points. Again, if you can't fit it on the graph, don't stress. If you can only get 3 on the graph, then get the 3 points that fit on the graph. All right, I'm going to pause for a second while we pull that up. It looks like this, and I'm going to grab the exponential functions worksheet right there. Okay. Now, we've got, since yours could have been on paper, we actually labeled, we labeled the points and stuff. But if you just look at the red graph compared to the blue graph compared to the black graph, black one is 2 to the x. Okay? That is your typical exponential function right there, that one. Okay? And it wants to know what transformations happen to get the other ones. So like to get this red graph, do you get it's kind of down, but it's also kind of to the right? So then you have to figure out what would the equation change to make the red one. y equals 2 to the x is a good start, but then if it got moved to the right, let's be specific. Does it look like it moved every point 2 to the right? Is it that simple? Here, compare this. This point and this point, is that 2 points to the right? This point and this point, isn't it 2 points to the right? I mean, it's also down, but it's 2 to the right. Aren't they all 2 to the right? Okay, so then you can use that and say if they're all 2 to the right, then it definitely moved like this, minus 2. Is that the only thing that happened? No, something else happened. If they all moved 2 to the right exactly, then it must have been 2 to the right. Did they all also move down 1? I think they all went down exactly 1 box. Down exactly 1 over 2. Down exactly 1 over 2, because that's at a halfway mark. So it looks like it's down 1 over 2. How do I do the down 1? Minus 1 on the end like this. By the way, don't ever go in and mess with this when you're moving things right or left or up or down. That is a stretch. You can stretch that number by putting something in front of it. All right. So I helped you get the red one. You figure out the blue one. I'll give you a hint. It's not just moved up 3. Think about this. This one's moved up 3, but that one's not moved up 3, and that one's not moved up 3. So don't try to do this by moving it up. What else makes something go up besides just sliding it up? Stretches. So you figure that out. All right. So let me clear this off, dragging this down a little bit. Okay, same idea on this one. The black one's the normal one, and that was this 1/3 x. It's decay. And then you got to figure out what happened to make it do this. And it's not just moved up. Is it just moved over 1 and up? Is it some kind of a stretch? That's what you have to figure out. And you can prove it by looking at the numbers. You can say, well, 0, 1 turned into that. See what I mean? The middle of the points turned into the other middle point. And how does 0 turn into 0.5? Well, that moved to the right a half. That could explain that. How does a 1 turn into a 2.33? Well, and it moved up, but it didn't just move up in a simple thing. All right. I'll let you figure it out from there. Let me see if there's any you can skip. Then that's all I have for you for the video.